All right, so I'll share my screen. Let me know if you can see it. Okay, so is the screen visible for everyone?
Yes, sir.
Okay, good. So this was the problem that we were doing in the last class. And so I think we were doing this part, right? We are finding the mass. So is there, before we proceed any further, is there any question that you might have from this past paper session? Anyone? Does anyone have any question? Okay, so I'll assume that there is no question. So this is what we were doing. I'll just quickly revise this part B. We had that the Earth was considered as an isolated sphere of radius r, and its mass was concentrated at its center. And we were given a graph whose potential was being varied with distance from the Earth. Now, this distance is from the center of the Earth. And this is how the potential varies. So you can read off your distances and potential. So you can read off your potential really compared to the particular value of a distance. And all of these distances, as you can see, are given in terms of r. So we have 0, r, 2r, 3r, 4r, and 5r, where r is the radius of the Earth. So we were given that by considering the gravitational potential at the Earth's surface, so at the Earth's surface, we know that the distances r, determine a value for the mass of the Earth. So what we did was we looked at this graph. We saw wherever on x-axis we have r, we drew a perpendicular line until it touched this point on this curve that you can see over here with this black line. And then we read off the value for potential. We found it to be equal to minus 6.3 times 7 by just reading it off this graph. So that's the value for potential. And we know that potential is written as minus gm by r. So all we did was we used this expression to write an expression for mass, which is minus phi r over g. And the value for phi from the graph, as we read, is minus 6.3 times 7. Just putting it in here, we were doing this, and I guess the class was over last time. So this is minus 6.3 times 7, but now we have to multiply this with r, but r is what? The radius of the Earth. So it is given over here, it's 6.4 times 6 meters. So just putting in the values really now, 6.4 into 10 raised to power, it was 6 meters, and divide this expression by the constant, which is 6.67 into 10 raised to power minus 11. Just do the math and you'll find the mass of the Earth. So is that clear? Is there any question in this part of the problem?
It's clear.
Okay, great. So in the next part, we have a meteorite is at rest at infinity. So at infinity really means that it's very far away from the Earth. So we say that it's at infinity. And it is at rest means that the velocity of the meteorite is initially 0. Now it's saying that this meteorite travels from infinity towards the Earth. So here we have the Earth, and here is this meteorite. It's very far from the Earth, and initially this is at rest. But after some time, it starts traveling towards the Earth like this. And we want to calculate the speed of the meteorite when it is at a distance of 2r above the Earth's surface. So we want to calculate the speed of this meteorite when it's 2 times the radius of the Earth. So maybe it's like somewhere in this region. So when it reaches, this meteorite reaches this point, which is, well, you can say it is approximately, let's say just 2r given in question. We want to see what would be the speed of this meteorite when it is at this particular point. So anyone in the class who would tell me how would we go about this problem? How can I find the velocity of this meteorite, which was at one point, it was somewhere very far from the Earth, and now it is at some point which is 2r from the center of the Earth?
We compare
So
both the forces. Gmm upon r square is equals to mv square upon r. We compare those.
okay, so that is almost right. You can, but think about this thing. At this point, the meteorite, there is no information that the meteorite is in the orbit of the Earth, right? So you don't know if this meteorite is in the orbit. It's all you know, it's very far. So of course, if it's at infinity, it will not be orbiting the Earth. That's the first clue. Second is, even if it comes 2r near this Earth at a distance of 2r, you're not provided with the information that it starts orbiting the Earth. You're not given that information. So at this point, if you say that the force of gravity is the resultant of this circular motion, which is the circular force, which is mv squared by r, then it does not make sense at this point, because you don't know that it is indeed going to travel in a circular path. So, I mean, this thing, because of this reason, this thing will not work, right? So, I mean, you suggested this, and even though you got it wrong, it's not, you learned something, right? So you can think in terms of this thing that while it's not in the orbit, so there is no circular force on this meteorite. Anything else that you might think? Or anyone from the class, anything else that I can apply to this system? So think of it like this. It is very far from the Earth, right? So it is very far from the Earth at infinity. So if something is really far like this, and then it is coming closer to the Earth, so you can think of something like, yeah, exactly, in potential energy. So something is very far from the surface, it will have some potential energy, and it starts coming closer. So that potential energy will convert into the kinetic energy, because it's moving now, right? So the only energy that can be converted into kinetic is that potential energy it started with. So everyone understands this?
Yes.
Yes.
All right. Okay, good. So we'll use the expression that will say that when it is at infinity, it has some, there is some potential energy which will be lost eventually when it starts moving. So we'll say that the loss in potential energy is equal to the gain in kinetic energy, right? So, well, we can do this thing simply by having here half m v squared, right? That's the kinetic energy, and the potential energy is really, remember, potential energy is just the potential times the mass, right? Or you can write it like this, it is minus gmm by r. But this thing, this minus g, let me use this thing. So this thing is just the potential function, right? So it is just phi. So if this is just phi, then this is really this is really phi times m is equal to half mv squared. Now m will cancel with each other, right? Because there is m on the both sides of this equation, which really tells you that the velocity is just 2 times phi, because I'm just making velocity the subject and then the square root of this thing. So is that clear for everyone?
Yes.
Okay, so now the question is then, what value of phi will I use, right? So what is this phi? So the answer to that is very simple. It comes from the question itself, because he's telling you at a distance of 2r, which means that I need the value of potential at this distance. Remember now that you are given a graph which relates these two things, distances and potential. So I'll just go and look at this thing. Oh, I have a 2r over here. I'll just drop a perpendicular, and when it meets this curve, I'll start going in the horizontal direction, and I'll get somewhere around here. And the value for potential here is, this is minus 2.0. So it would be, well, you can use, it's 2r, right? So it will be something that's 2.9, right? Something around about 2.9. So now, but you get the point, right? So you'll just read off the value of phi from this thing, and you'll put it over here in this expression. So do you understand how will I find the value of r? Sorry, how will I find the value of phi? Is that clear?
Yes.
All right. So then you'll just put it in this expression, and you'll compute the velocity by just having the value of phi in this expression, right? And the rest is just math. So is that clear for everyone?
Yes, sir.
Okay, great. So then we'll move on to the next question, next part really. And here we have that in practice, the Earth is not an isolated sphere. It's okay, so that's true, because it is orbited by the moon, as illustrated like this. So I mean, of course, the Earth, there is this moon which orbits the Earth. So that means that the Earth is not just isolated, it will also experience the force of gravity due to this moon. So the initial path of the meteorite is also shown. So here they're showing you that here we had this meteorite, and it moves like this, and it's moving towards the Earth. Suggests two changes to the motion of the meteorite caused by the moon. So because there is gravitational field due to Earth over here, but there's also some gravitational field because of this moon present in the orbit of the Earth. So what do you think could happen to this meteorite's motion when it's approaching towards the Earth? If there is this moon also present which is orbiting the Earth? Anyone, any suggestion? What could happen?
It could accelerate faster
Exactly, that's one point. So what would be your reason for that?
because there would be double the gravitational force acting on it. Not double, like
Yeah, so the right,
addition.
exactly. So there is, yes. So the resultant of the Earth and Moon, there would be more gravity that would be affecting this meteorite. And if the force is more, that means the acceleration is going to increase, right? So yes, of course, the acceleration would increase, would be higher. So that's one. Any other reason? So this also implies that the velocity would be high, right? So this just comes under this. So velocity would also increase of the meteorite, velocity of the meteorite, right? So the same, so this is just one point. If you say velocity, you cannot really say that acceleration would be higher here and then velocity would be higher. I mean, you can, but they both really mean the same thing. So it's not really sensible to say, because acceleration, higher acceleration implies that velocity would be high, the new velocity. So any other reason? Any
It
other
could hit the
change?
moon.
Yeah, sorry.
It could hit the moon.
It could hit the moon. Okay, so that's I mean, yeah, maybe it could hit the moon. Very there's a chance for that to happen. So your answer could be framed in this way as well, that the path of the meteorite, they're really talking about changes to the motion of the meteorite, right? So I mean, it doesn't make sense if you say it could hit the moon, but you could say, you could frame the answer in this way, that the path or the motion of the meteorite would be affected in this way, that it would, instead of directly going towards the earth, it might deviate from its path due to the field of the moon as well. So it would, you could say that the path would deviate from its original path, whatever the spelling is of original path. So is that clear? Does that make sense?
Yes.
Okay, great. So is that okay with everyone?
Yes, sir.
Okay, good. So the path would deviate in this way, that it might be coming closer to the earth, but there is now force due to moon as well. So it might be, it might go something like this, and then it might go something like this. Well, it could deviate in multiple ways, depending on the position of the moon, really. So the path could deviate. So great. So that's this. And then we'll move on to the next question, which is question number 4. An isolated star has radius r. The mass of the star may be considered to be a point mass at the center of the star. So we have a star which is isolated, meaning that there is no other forces acting on the star, and the radius of this is r, and the mass is considered to be a point mass. Now, the gravitational field strength at the surface of the star is given as GS. So this is the gravitational field strength. On figure this, sketch a graph to show variation of gravitational field strength of the star with distance from its center. You should consider distances in range r to 4r. Okay, so what do you think? What would this graph look like? Do you understand what we have to do? Hello, can you hear me?
It would be increased.
Okay, so you have to think in terms of the gravitational field strength, right? So what do we know about gravitational field strength? It's G is equal to, what is the expression for it? It's GM,
GMM
right?
upon R
GM,
square.
yeah, so GM by R, right? R squared. Right. So what could I, what is the shape of this graph that I could expect?
Curve.
decreasing.
Would it be a straight line or would it be a curve?
Curve.
Yeah, so it would be a curve. So that's good. And curve, how would it curve really? Or you can just tell me, would it look something like a curve that I have from y is equal to 1 by x squared graph? If I look at a mathematical expression of this, would the graph be this one?
A decreasing curve.
Yeah, so the curve should really look like a curve that you expect from a 1 over x squared graph, right? So what you could do is you could pick values in this. So suppose that I could say that you could pick, first of all, you could pick a value of 0 at r. So you could say maybe r is 0. What happens when I put r0 in this expression? I get g tends to infinity, right? So g is very large when r goes to 0. Is that okay with everyone? Because I'm really dividing by 0, right? So dividing by 0 really means nonsense, but it also means that if I'm saying that on the right hand side I have a dividing by 0 thing happening, then the left hand side is going towards a very big value. So is that clear with everyone that when I say that r is 0, g tends to infinity, or g will be equal to infinity? Now, using the term equal to is not sensible when you're talking in terms of infinities, but yeah, so g tends to infinity.
Yes, it's clear.
Right. So you would really have an asymptote like thing going on over here. So it would not be touching the y-axis, but it would keep on moving parallel to this axis. So it will be something like this. So for example, if I draw it separately, if I draw this thing that at 0, it's infinity. So it would really be something which is going to the infinity. If it's positive, then you can just say that it's like this, right? So it's like this. Now it's never going to touch this y-axis. It will keep moving parallel to this axis. That means it's like very large, it's infinity. So we can do the same thing over here. Note that there's no negative values for this, so we'll say that it's like this. It's never touching this thing. And because now maybe use a value, maybe C for 2r, then you can put it in, so you'll get something of okay, so are you given the mass of this star? You're not given the mass, so you can draw a rough sketch, right? So you'll just sketch the graph, which looks something like this. I mean, it's not a very nice picture of the graph, but do you agree with this thing? I really drew this thing because if you look at the graph, which is of y equals 1 by x squared, it's like this. And the reason for that is because g and m are constants. So only we are seeing that how does my g change with varying the distance r. So it will look something like this, which is the graph of y equals 1 by x squared. So is that clear?
Yes.
Okay, great. So then we can move on to the next part, which I assume is this one. Okay, so now the next part is we have that the Earth and the Moon may be considered to be spheres that are isolated in space with their masses concentrated at their centers. We have really gone through the statement so many times, so we now know what it means. The masses of the Earth and the Moon are 6 times 10 raised to power 24. So that's the mass of the Earth. And for the Moon, we have 7.4 times 22 respectively, right? So these are the masses of the Earth and the Moon. The radius of the Earth is this, and the separation of the centers of the Earth and the Moon is 60 times this. So they have given you the radius in terms of the radius of the Earth, and then the separation between Earth and Moon is given in terms of the radius of the Earth. And they have given you a figure, so you can just have a look at it. Now, looking at this figure, explain why there is a point between the Earth and the Moon at which the gravitational field strength is 0. So how can that be possible? Why is there a point in between these two objects where the value of G would just become 0? Anyone? You can think in terms of forces as well, or even in terms of
At
gravitation. No, they're saying that the point lies in between these two. So it will be in this region of 60 times RE. Somewhere in between this, there will be a point at that, and in that region, the value of G would be 0 at that particular point. So we need to tell why is that even possible. Anyone? Any comment on this? Doesn't matter if it's wrong. We'll figure it out, right?
Sir, the mark would be towards the moon.
Okay, and why would you say that?
Because Earth has a greater gravitational field than the moon.
Okay, right. So although that might work, yes, but why at that mark, why would the gravitational field strength be 0? What's that reason for that, really?
As the force of the Earth is equal and opposite to the force of the moon.
Exactly. So that's a very good point. Now, yes, you can talk in terms of forces as well. So because if you look at the vector pointing from the Earth to the moon, and so if I draw this line, now the force is attractive. So the vectors would be pointing in these directions, right? So because the forces, or you could also talk in terms of gravitational field strength, they are in the opposite directions. That's why when you will add these two, so this would be a positive thing and this would be a negative thing. Now these would have their own values, but at one particular point, these two values might be equal, and when they are equal, adding these two values would just means that adding positive and negative, which would vanish. So that's the reason that the gravitation there can exist a point in between these two objects where the gravitational field strength would be 0. Right? So does that make sense? Is that clear for everyone?
Yes.
Great, good job. Okay, so that's this thing, and let's see, do we have anything down here? No. Okay, so next part of the question is determine the distance in terms of the radius of the Earth from the center of the Earth at which the gravitational field strength is 0. So we want to determine the distance of this point from the center of the Earth, right? And we'll write it in terms of RE, which is the radius of the Earth. So we don't have to put in the value of radius of the Earth. We'll just give our answer in terms of this value. So we don't have to do the math, heavy mathematics, really. And not heavy mathematics, that's a very far statement to say. It's just putting in the values in, but we don't have to do that. So any idea how would we go about this problem? We need to find the distance of this point in terms of radius of the Earth from the center of the Earth. So how will I do this thing? Where the gravitational field strength is 0. We'll use this same this knowledge of you can use the knowledge of force, or you can use the knowledge of gravitational field strength. You defined it in this way, that the forces are equal and opposite, right? So I can say that the force, one of the forces would be G m by r, or let's just call it any other variable. Let's call it x squared, or it doesn't matter, you can call it r squared, is equal to G m, where note that over here the one of the mass is of the mass of the Earth. So if I'm considering here, capital M is the mass of the Earth and small m is the mass of the Moon. Now, because we're now our thing that how do I say this? The major part, as they have mentioned in the question, is the Earth, because we want to find from the center of the Earth. So the major part is the Earth, and Moon is the small mass or the test mass, which is being, you can say, in the field of the Earth. So because we are considering it as an Earth, so capital M is the mass of the Earth over here, small m is just the mass of this object, Moon, and this is the force for mass of the Moon, and this is again the same mass, which is of the Moon. So this mass can really, one of the masses can just go away in this way, that this mass will cancel with this one, and here we have r squared again. But this would not really be r squared, because the distance for this Moon would be some distance, you can say any distance minus this r squared. Actually, it would be this minus this times the squared of this thing. And the reason for that is because what do you think? What would be the reason for using when I wrote the expression for force for the Moon? Why did I write it in terms of d minus r?
Because that point is somewhere between these two.
Yeah,
planets.
exactly. Good, very good. So now this expression really becomes the expression for gravitational field strength, right? Because one of the m goes away, so this expression is really an expression not for a force anymore, but the expression for the gravitational field strength. And here we have this equation. Now our goal is to find out the value of r. So we can do that simply by putting in some of the values. We know the mass of the Earth and the mass of the here we were given these, right? So let me just show you. So here we were given these values. Here is the mass of the Earth, and this is the mass of the Moon. So we'll just put in these values. G can also go away because it's just a constant and it appears both sides of the equal to sign. So putting in the values and solving this equation for R would give you the answer that you want in terms of RE. So is that clear? What would be the value for D, by the way? It's this total distance, right? So you'll have put in place of D, you will have 60 RE. And so that's where you get this in terms of RE, and then you'll get a value by solving this equation. So this G's go away. We have the values of the mass of the Earth. We have the value of the mass of the Moon. We have the value of D, which is 60 RE, and we have to find R. So everything is known, but we just have to find R. So we'll just rearrange this expression and we'll write the value of the R. So is that clear? Or is there any question? Yeah.
So both the
Yes.
capital M's are different.
Yes, I've written with the subscript. This is mass of the Earth, right? And this is mass of the Moon. Because this came from using the force on the Earth, and this came by using the force on the Moon. Or we could have directly talked in terms of gravitational field strength, saying that this would be equal to this, right? Earth would be equal to Moon. So we could have gotten it from there. We would have directly written this equation, or if we talk in terms of force, then we just cancel out something that we again come back to the gravitational field strength expressions. So now it's just a matter of putting in the values of mass of the Earth and mass of the Moon, and the value of D, which is the total distance between these two objects, which is given in the question as 60 times radius of the Earth. So just put in the values and write your answer in terms of radius of the Earth. So here you'll have a number. And so is there any question?
No, sir.
Okay, so is that clear for everyone in the class?
Yes.
Okay, great, wonderful. So before we go any further, can you let me know what time is it? I mean, not what time is it, I can see the time. I mean, how much time is left? Because that I cannot see.
Less than a minute.
Less than a minute. So which means that the class will be over anytime now. Yeah, so just I've sent you some worksheet, not some, but a worksheet. And it's okay if you did not do it yet. Just take your time, not too long though, but do it yourself. Do the worksheet yourself. Maybe use helping material, use your book, go through some things, understand them, and try to do the worksheet. And then we'll discuss it in the class. So when you're doing the worksheet, you will see that you will have some problems. You'll even have some problems in your conceptual understanding as well. And then you can note them down somewhere, and we can discuss all of those in a class that we can have maybe on Friday, perhaps on Friday.